This chapter concerns metrics, LLM judges, and statistical confidence. Begin by defining the metric from the operational failure. A judge can report that a revised real estate assistant improved while quietly rewarding longer answers. If the underlying failure is an unsupported listing claim, the practical consequence is more serious than a noisy score. The team may ship a system that sounds more helpful while making claims the listing data does not support. Start with the failure, not with a favor evaluator. Next, translate the operational failure into a criterion. Suppose the assistant says, the property has a renovated roof and dedicated guest parking, when the sandbox listing contains neither fact. The answer is low quality, is too broad to diagnose or operate. The actionable criterion is narrower. Every factual claim about a listing must be supported by the records available to the assistant, or be explicitly marked as unknown or uncertain. This criterion has an explicit positive class. A claim is a positive instance of supported_listing_claim only when the claim is entailed by the permitted listing evidence. A claim is not positive merely because it is plausible, common for similar properties, or consistent with an external real estate convention. It is also not rescued because the rest of the response is useful. The evaluator must distinguish supported, unsupported, and, where the data contract permits it, not verifiable. This translation connects an observed failure to a decision. If unsupported claims increase after a prompt, retrieval, or model change, the team has evidence to investigate that change. It does not yet have evidence that the entire assistant is better or worse. Before choosing a score, decide what unit will be measured. Use 2 units of analysis. At the claim level, extract each checkable listing claim and compare it with the available evidence. This shows whether there are one or many unsupported details. At the response level, mark the response if it contains at least one unsupported listing claim, which aligns more directly with a release guardrail. The response level label should come from the labels assigned to individual claims, rather than from an independent impressionistic judgment. A claim receives the positive label when the allowed evidence supports it. A claim receives the negative label when it asserts a listing fact that the allowed evidence does not support. Use the boundary label when the claim cannot be reliably mapped to a listing fact or when the evidence contract does not determine its status. A response receives the positive label when none of its claims is labeled unsupported, while applying the project's specified treatment of boundary cases. A response receives the negative label when at least one of its claims is labeled unsupported. Record the extraction policy as part of the metric. Subjective marketing language, such as the home is bright, may be outside this criterion, while the home has south-facing windows is a checkable property claim. A statement about qualifying for a buyer's loan is not a listing fact and belongs to a different risk and evaluation contract. The metric becomes unreliable if the labeler silently changes what counts as a claim. The companion artifact must specify the criterion, positive class, evidence source, boundary policy, and aggregation rule in a machine-readable file. This YAML defines a claim-level metric for detecting factual property claims that exceed permitted evidence. It declares the labels permitted evidence sources, evidence policies, boundary rules, aggregation rules, and provenance fields. The prohibition on unsupported world knowledge is narrower than a blanket ban on inference. It blocks model invention, outside knowledge, and unsupported assumptions, while allowing a claim to be supported when it follows from permitted records under the documented extraction rules. At the claim level, every extracted claim remains in the denominator and not _verifiable is reported separately rather than silently counted as supported. The specification must be tested rather than used to hide ambiguity in one number. A repository test should load the YAML, confirm that the positive class is declared, require claim as the unit of analysis, reject an empty evidence contract, and reject a missing entailment policy. The implementation should use the previously established shared claim schema, fixtures, and sandbox records, importing those modules instead of redefining a second listing representation. This executable boundary loads and validates the metric specification, then evaluates the pinned 5-claim fixture. The loader checks the declared labels, claim unit, allowed evidence sources, both evidence policies, and required labels. The evaluator counts each claim label, retains the number of claims as the denominator, and marks the response failed when an unsupported claim is present. The imported fixture contains 5 claims under the shared schema. 3 are supported, 1 is unsupported, and 1 is not verifiable. The repository test should verify the resulting report and also exercise schema failure with an invalid specification. These tests assert both evaluation behavior and validation failure. The first test loads the specification and checks the 3 supported, 1 unsupported, and 1 not verifiable counts, a denominator of 5, and a failed response caused by an unsupported claim. The second test supplies only a positive class and claim unit. Loading it raises a value error because allowed evidence sources are missing. These checks prevent a malformed specification from silently producing a release result. The evaluator keeps supported, unsupported, and not verifiable as separate reported categories, retains all 5 extracted claims in the denominator, and applies the response guardrail only to unsupported claims. With the pinned YAML parser and the repository's locked dependencies, the command pytest qtest/test_listing_metric.py should produce the stated test result. The supplied code implements the shown operation. Running the module against the stated fixture should produce deterministic output equivalent to the stated result. The supplied code implements the shown operation. The 3 supported claims remain visible as the positive count. The 1 unsupported claim makes the response fail, and the 1 boundary claim is reported separately for review. The denominator is 5 because all extracted claims are counted. Any later review-adjusted rate must document its own denominator rather than silently replacing this one. In a clean companion repository environment, run the test with the pinned dependency lock file and shared sandbox fixture. No credentials or external side effects are required. Why omnibus quality scores fail here? A score such as quality 8.4 combines factual support, relevance, completeness, tone, policy compliance, and perhaps usefulness, even though these dimensions require different evidence. Longer answers can receive more opportunities to appear complete, and a judge may reward elaboration while the probability of an unsupported detail rises. A single score cannot show whether retrieval failed, extraction over-generated claims, the response exceeded the evidence contract, or the evaluator prefer verbosity. Keep the dimensions separate. For the real estate assistant, listing _claim_support_v1 should sit beside independent criteria for answer relevance, required disclaimer behavior, and tool use correctness. Each criterion can have its own unit, label semantics, adjudication process, and release threshold. A composite decision may eventually be useful, but it should be built from visible component results with an explicit policy rather than substituted for them. The neighborhood feels welcoming should not be forced into a supported or unsupported label. Mark it not verifiable. Apply the required human review workflow and determine separately whether the language is prohibited by policy. If no review workflow exists, treat the metric as incomplete rather than claiming review occurred. The evidence can support a focus comparison, but its conclusions must remain within the specified evaluation contract. Under a specified fixture set, evidence contract, claim extraction rule, and aggregation policy, The artifact can show that one assistant variant produced fewer responses containing unsupported listing claims. It can prioritize investigation when failures coincide with retrieval, generation, or claim extraction instrumentation, but the metric alone cannot localize causality among those stages. It provides an evaluator owner with a stable contract to validate. This metric cannot establish that the assistant is generally accurate, safe for every real estate interaction, compliant with applicable housing or transaction rules, or superior for users whose questions differ from the sample cases. Results can fail when fixtures omit relevant fields. Claim extraction misses implicit assertions, evidence changes after labeling, or a judge treats plausible language as entailment. LLM-Judge rationales are diagnostic annotations, not proof of correctness, so critical samples still require defined human adjudication. This specification is the handoff artifact between a reported failure and an executable check. It gives code owners a contract to test, platform owners a schema to version, and product and safety owners a criterion whose decision boundary they can review. Release Evaluator Suite v1 with validation results, boundary examples, known failure modes, and a model card for each automated judge. Before trusting any system comparison, give each operational failure one named criterion with an explicit positive class, declared unit, and documented aggregation rule. The next step is to choose the evaluator that can actually answer the measurable criterion. For the property recommendation email, schema validation can establish whether required fields are present. Database checks can establish whether cited facts match approved records, and an LLM-Judge can assess semantic properties such as relevance or unsupported implications. These instruments answer different questions. Choosing the wrong one can make a passing score appear to support a claim it never measured. An evaluator is a measurement instrument with a failure profile, not simply a scoring function. Choose the least interpretive instrument that can establish the criterion, then add other instruments when the criterion has independent parts. The decision is not which evaluator is most sophisticated, but what evidence is sufficient for the claim. Evaluator selection begins with the least interpretive option. An executable evaluator applies a rule whose result is directly computable, such as checking a required field, permitted range, schema match, or approved database identifier. It is usually preferred for hard requirements because its inputs, logic, and failure output can be inspected. A reference evaluator compares an output with an authoritative expected value or set of values. It can verify a listing ID, transaction status, or require disclosure. References need provenance, versioning, and explicit treatment of multiple acceptable answers. Appearing in a fixture does not make a reference authoritative. A classifier assigns labels such as an unsupported property claim or prohibited recommendation. It is useful when labeled examples and a repeatable boundary exist, but both labeling and classification can introduce errors. Its threshold and abstention behavior must be specified. A judge assesses relationships, such as whether an answer addresses the question, follows a nuanced policy, or is supported by supplied evidence. Its rationale is diagnostic annotation, not proof of correctness. It must be tested against adjudicated examples, including adversarial and borderline cases. A human evaluator is the reference point for consequential, ambiguous, or difficult to formalize questions. Because review is slower and can vary across reviewers, it needs a rubric, sampling plan, adjudication rule, and disagreement record. Its value is an accountable process for distinctions automated instruments cannot yet establish reliably. A compact selection rule is: for output shape or required fields, choose an executable check and add human review for consequential exceptions. For exact identity, values, or database state, use a reference or database check and add human review for stale or conflicting records. For known policy categories, use a classifier and human adjudication for borderline cases. For meaning, relevance, or evidence support, use a judge with reference checks and sampled human review. For high-consequence ambiguity, use human evaluation and deterministic checks to reduce reviewer burden. The table is a decision aid, not a hierarchy of quality. A judge is not an upgraded schema validator, and human review does not replace a check that a database can answer exactly. Prefer business logic when that business logic is the requirement. Deterministic checks should carry as much of the criterion as possible. Compare every cited listing identifier with the approved search results, resolve prices against the current sandbox record, and search for required disclosures using a version normalization policy. These checks are fast, reproducible, and easier to debug than a global quality score. In the email scenario, the schema validator catches a missing recipient and malformed fields, while the database check catches a fabricated price or address. Neither determines whether the prose accurately conveys the evidence or answers the request without an unsupported implication. Those remaining questions justify a semantic evaluator, not replacing the first two checks with one. Decompose the evaluator artifact instead of using one email quality score. Record separate results for contract validity, record grounding, required disclosure, supported claims, and response relevance. Give each result its own owner, input contract, failure examples, and escalation path. Aggregation can then distinguish a hard failure from a case that passed hard checks but requires semantic review, rather than hiding both in an average. Use learned evaluators only for semantic work. Learned evaluators are appropriate when the criterion depends on meaning rather than literal form. A judge may assess whether a response accurately explains a listing constraint, distinguishes known facts from uncertainty, or answers a multi-part request. A classifier may identify a recurring category of problematic language after that category has been defined and labeled. Calibration is not a one-time prompt writing exercise. Use a fixed rubric, representative positive and negative cases, boundary cases, and comparisons with adjudicated labels. Test whether the judge favors verbosity, particular writing styles, or answers that repeat the rubric without satisfying it. Include concise correct answers and long answers with subtle unsupported claims. Track abstentions and disagreements instead of forcing every sample into a confident binary result. In the email example, the judge receives the user request, approved listing evidence, the generated email, and explicit criteria separating relevance, supported claims, and unsupported inferences. It should not infer database truth from prose alone. The judge model card is the artifact that changes. It documents intended use, calibration data, known biases such as verbosity preference, failure conditions, and cases requiring human adjudication. Its explanation may help an engineer locate a defect, but the criterion and evidence are still needed to establish that the defect exists. When a release criterion spans different kinds of truth, evaluate it with complementary instruments rather than relying on one evaluator. A single evaluator cannot establish acceptability for release because that criterion spans structural validity, factual grounding, policy constraints, and usefulness. A schema check establishes only structure. A database check establishes only selected facts. A judge may assess relevance and unsupported implications, but may miss a record mismatch. And human review may resolve ambiguity without manually verifying every exact field. The combined evaluator must keep component results visible. A failed database check cannot be offset by a high judge score, and semantic disagreement must remain visible even when deterministic checks pass. A missing optional stylistic preference should not block a valid message unless the release policy makes that preference a hard requirement. An email with no property claims may pass grounding because it contains nothing to contradict, yet still fail a request to compare two listings. Therefore, having no unsupported claim is not the same as being helpful and complete, and a clean score on one dimension cannot serve as evidence for another. Evaluation evidence supports bounded conclusions, not broader claims than the suite represents. For the cumulative real estate assistant, Evaluator Suite V1 includes version schemas, database assertions, semantic criteria, calibration results, boundary examples, known failure modes, and a model card for each learned judge or classifier. It can support a bounded statement that variant be reduced failures on a defined email criterion under a specified fixture and review process. It cannot establish general accuracy, safety across all real estate interactions, legal or policy compliance, or superiority for unrepresented users and data. Failure conditions include stale references, incomplete fixtures, ambiguous rubrics, classifier drift, judge sensitivity to wording or length, reviewer inconsistency, and domain examples lacking appropriate privacy and real estate review. When the consequence is material, sample failures for human adjudication and preserve the evidence shown to the reviewer. This is daily engineering work, not an academic appendix. AI engineers and evaluation engineers maintain criteria and calibration sets. ML platform engineers version runners and artifacts. Product engineers connect evaluator outcomes to release gates. And safety engineers inspect boundary cases and escalation paths. The shared deliverable is a defensible measurement contract, not a leaderboard number. The operational rule is to select an executable, reference, classifier, judge, or human evaluator according to the question it can actually answer. Prefer deterministic business logic, reserve learned evaluators for semantics, and combine instruments without allowing one score to conceal another failure. Release Evaluator Suite V1 only with its validation results and a model card for each judge. Then implement the fast, transparent checks that should never have required a learned evaluator. This section addresses scores implemented with explicit code. Before celebrating an apparent improvement in the real estate assistant, verify whether the recommended home is within the buyer's budget, has the requested number of bedrooms, and is addressed to the intended recipient. Also verify whether the sandbox recorded an email as sent rather than relying on the assistant's claim. Without explicit checks, a judge can reward longer and more persuasive answers that still violate the task. The practical consequence is immediate. Hard requirements should fail loudly, explain why, and remain inspectable without an LLM. A code-based score does not replace semantic evaluation. It handles requirements whose meaning can be represented as data, including structure, membership, ranges, state transitions, and prohibited content. The contract must be expressed through executable checks. For the cumulative real estate assistant, the evaluator receives the repository's normalized response contract, the fixture describing the request, and the sandbox event trace produced by the shared tool adapter. The established boundaries are normal as _listing_response, load_fixture, and sandbox.events. The scorer accepts their mapping and sequence protocols instead of defining a second application schema. A repository boundary adapter can convert typed objects to these read-only interfaces without changing the scoring rules. The fixture can require a maximum price of $650,000, 3 bedrooms, the recipient buyer at example.test, a non-empty recommendation list, amenities drawn from parking, garden, and transit, and a sandbox email state of sent. The scorer evaluates each requirement independently. Useful checks cover structure, sets, ranges, state, and prohibited content. Structure checks verify required keys, expected value types, and non-empty recommendation lists where the contract requires them. Set checks verify that every listed amenity is allowed or that every required feature appears in the response. Range checks verify that price is at or below the requested maximum. Bedrooms meet the minimum, and numeric values are finite and within domain bounds. State checks verify the expected tool result status, require an email identifier only after a successful sandbox send, and preserve the recorded tool state against a later assistant claim. Prohibited content checks detect disallowed fields, unsafe instructions, fabricated transaction claims, or restricted terms under a versioned, reviewed project policy. A pattern match is not a legal or fair housing classification. A scorer should report check-level evidence rather than only an aggregate, such as 0.75. Each check identifies its name, expected value, observed value, pass or fail status, and, when useful, its location in the response or event trace. This makes failures actionable and helps reviewers distinguish a bad recommendation from a broken fixture or parser. The supplied scorer evaluates a normalized listing response and ordered sandbox events, returning structured evidence with names, statuses, expected and observed values, paths, and messages. It checks structure, sets, price, and bedroom constraints, the recipient, the latest email event, and prohibited content patterns. Invalid patterns fail the policy check and matches fail response checks. The tests cover passing and failing responses, a later failed email event, the price boundary, and a malformed price type. However, as written, the tests do not run. The fixture passes tuple values such as int float in required underscore types, while underscore check underscore structure accesses expected underscore type, underscore underscore, causing an attribute error. The scorer also does not check for an email identifier after a successful send, despite that stated state requirement. The complete code block is supplied in source beat 0080. Key phases are the evidence models, lines 10 to 29, structure checks, lines 36 to 64, set checks, lines 67 to 91, policy validation, lines 94 to 100, latest email state, lines 103 to 110, scoring flow, lines 113 to 175, and tests, lines 190 to 220. The implementation separates immutable evidence from the aggregate result. Numeric validation rejects Booleans and non-finite values. Structure checks distinguish missing fields from incorrectly typed fields and can require non-empty recommendation lists. Set checks report unexpected amenities and missing required features. The shared fixture loader supplies only the constraints relevant to each task. Events arrive in the shared sandbox's monotonically increasing order, and the final relevant email event is authoritative. Therefore, an earlier sent event followed by failed does not pass. This models the state visible to the evaluator, not delivery to a human inbox. If ordering uses an explicit sequence field, the adapter must sort or validate it before calling the scorer. Without guaranteed ordering, the scorer should fail closed rather than infer state from an arbitrary list. The negative fixture verifies evidence-bearing failures for structure, non-empty list, set, budget, bedrooms, recipient, final email state, and prohibited content. The boundary fixture confirms that exactly $650,000 passes and at most contract, while the string $650,000 fails because the scorer does not silently normalize it. Running the file produces the following result. The scorer test run produces the exact output, scorer tests passed. The cumulative repository artifact includes the version scorer, shared fixture contract, normalized response adapter, positive and negative fixtures, sandbox event contract, and report format. The adapter should use the repository's established schemas, fixture loader, and sandbox event types. Production use pins the interpreter and dependencies, runs tests in a clean environment, and keeps provider-specific adapters outside this durable core. Consequential tools remain sandboxed. This scorer requires no credentials and performs no external side effect. A passing application fixture alone cannot establish that the scorer is correct. Mutate one field at a time. Remove a required key. Replace a number with the wrong type. Empty the recommendations list. Add an unallowed amenity. Raise the price above the limit. Reduce bedrooms. Change the recipient. Alter the final event status to failed, or insert a prohibited phrase. Each mutation should produce the intended failure and evidence. Assertions should inspect check names together with expected and observed values, so a scorer cannot pass because it failed for an unrelated reason. Add boundary cases alongside mutation tests. A price exactly equal to the maximum passes when the contract says at most, while the string 650,000 fails unless normalization is explicitly part of the shared contract. Also test missing and empty lists. Duplicate set values if duplicates are prohibited, missing required features, and invalid prohibited regular expressions. The invalid expression should fail policy validation during setup rather than raise unexpectedly during report generation. The contract must define the intended behavior because strict scorers may reject harmless formatting variation, while permissive scorers may accept malformed data and hide defects. Prohibited pattern checks can miss paraphrases, other languages, or encoded text. Regexes therefore need versioning, review, explicit case policy, and representative fixture testing. These checks enforce reviewed project policy. They are not complete safety evaluators, legal classifiers, or fair housing determinations. For the tested fixtures, these checks can establish that responses met encoded budget, bedroom, recipient, structure, set, state, and prohibition criteria. They cannot establish that listing data is current, a recommendation is suitable, a policy interpretation is legally correct, or unrepresented users receive equivalent performance. They cannot prove that an email reached a human inbox. The sandbox event establishes only the state modeled by the test. Failures can arise from lost event ordering, production, evaluation normalization differences, or omitted paraphrases. When the consequence is material, preserve evidence and route ambiguous or high-impact failures for review. Maintaining a trustworthy evaluator is a daily responsibility across roles. AI engineers maintain score logic and fixtures. Evaluation and ML platform engineers version runners and artifacts. Product engineers connect hard failures to release gates. And safety engineers expand prohibited content and escalation tests. Engineers also maintain the adapter between cumulative application contracts and durable score interfaces. The deliverable is a trustworthy evaluator component whose limitations are visible. Release Evaluator Suite v1 with the scorer, its validation results, fixture coverage, event ordering assumptions, prohibited policy version, and a model card for each learned judge used elsewhere in the suite. Implement fast, transparent checks for hard requirements, return the evidence that caused each decision, and test both successes and deliberate failures. Use these checks for release gating and targeted debugging of encoded requirements, not for broad recommendation quality, legal correctness, inbox delivery, or semantic safety. Only then should a narrow, context-complete LLM-Judge evaluate what code cannot reliably express. The next design task is to create an LLM-Judge. A judge can report that variant B improved unsupported claim detection while actually rewarding variant B for writing longer, more persuasive emails. This can promote a release that invents listing details with greater confidence. The remedy is not a more elaborate rubric. Use a narrow, context-complete prompt with labels, evidence boundaries, and an output contract that make the intended measurement difficult to misread. The judge design should start by defining the decision to be made, rather than by choosing the model. For the real estate assistant, the immediate question is whether an email contains a material claim unsupported by the retrieved listings. The judge is not evaluating helpfulness, writing quality, legal safety, or likelihood of converting a buyer. Those concerns may require separate evaluators. Combining them here would make a failure impossible to diagnose. The criterion is defined through 4 parts: the evaluation unit, the positive condition, the negative condition, and what is out of scope. The unit is one generated email evaluated against one retrieval context. The positive condition holds when the email asserts a factual property of a listing and the provided listings do not support that assertion. The negative condition holds when every verifiable listing claim is supported by the supplied context, or the email clearly marks uncertainty instead of presenting the detail as fact. The evaluation excludes style, completeness, ranking quality, currentness of the database, and whether the recommendation suits a particular person. Use the labels supported, unsupported, and not underscore applicable rather than vague scores such as good or mostly accurate. Unsupported means at least one material factual claim lacks support. It does not mean the claim is known to be false. A missing garage field cannot prove that a property has no garage, but the email must not assert no garage as a retrieved fact. Next, set the evidence boundary in the prompt. The judge should receive the task instruction, the retrieved listing records, and the target email in clearly delimited fields. It should not receive hidden application metadata, the system's chosen variant name, or a conversation label that reveals which answer the experiment is expected to favor. State explicitly that the retrieved records are the complete evidence. General world knowledge and plausible real estate conventions are not evidence. Use the supplied field values exactly. A record stating bedrooms. 3 supports the claim that the home has 3 bedrooms, and price. $725,000 supports the stated price. A null underscore fee does not support saying there is no HOA fee. It supports only the faithful statement that the supplied listing details do not include an HOA fee. Require an evidence trail for each claim. It should identify the supplied field that was matched so a human can inspect the decision. This trail explains the audit path. It is not proof of correctness or private reasoning. The judge's rationale is also model output and must be validated like the verdict. The suite uses a durable prompt contract. This prompt defines the evaluator's factual support criterion, complete evidence boundary, boundary examples, and exact JSON output. Its flow evaluates the supplied email against the supplied listing records. It returns unsupported for any material unsupported listing claim. Supported when every material claim is supported or explicitly qualified, and not underscore applicable when no factual listing claim can be evaluated. It does not assume values for omitted, null, or unknown fields, while a claim that a field is unavailable is supported when the field is absent or null. The exact prompt is system. A downstream parser can reject unknown labels, missing keys, malformed evidence arrays, or extra pros. Parse failure must trigger retry or review rather than being silently converted to a pass. Use structured output when the provider supports it, while keeping the provider-neutral contract separate from provider-specific request code. Consider a case where the email makes a listing claim that the retrieved records do not support. The fixture has 14, Cedar Lane at $725,000 with 3 bedrooms, and 8, Harbor Street at $680,000 with a null underscore fee, but no supplied bedroom count. The email says, I found 2 3-bedroom homes. 14, Cedar Lane is listed at $725,000, and 8, Harbor Street has no HOA fee. The judge should return unsupported, identifying the unsupported 2 3-bedroom claim and HOA assertion. The null field is insufficient support for saying there is no HOA fee. It should not downgrade the email for enthusiastic tone. It should not reject the supported price claim merely because prices can change outside the fixture. If the email says the retrieved details for 8 Harbor Street do not include an HOA fee and ask the reader to confirm it, the claim is qualified and evidence-faithful. The judge should return supported, even though the email does not determine whether a fee exists. The labels therefore distinguish an unsupported assertion from acknowledged uncertainty. The target identity should remain hidden where possible. Present candidate outputs as response_A and response_B randomize their order during pairwise experiments and evaluate each response independently against the same retrieval context before comparing results. Do not tell the judge which system is new, larger, cheaper, or expected to win. Hidden identity reduces one obvious source of preference leakage. It does not eliminate verbosity, position, or self-preference biases, which are addressed in the next section. A provider-neutral adapter. The adapter separates the durable evaluator contract from any vendor SDK. Its mock transport makes the example executable without credentials or external side effects. The adapter defines a transport contract, a typed verdict, and a structured judge. The judge rejects empty or non-string emails, builds a user message from retrieved listings, and the email sends that message through the transport, parses the response as JSON, and checks the exact top-level schema. It then validates the label, claims, claim fields, claim statuses, text, evidence list, and evidence entry types before returning a verdict. The mock response is unsupported. The fixture contains a null HOA fee. The assertion checks the label, and the final print output's unsupported. The expected output is unsupported. The adapter validates the boundary between model output and measurement data. It does not validate whether the model's substantive judgment is correct. Production testing should include pinned dependencies and contract tests for valid output, malformed JSON, extra keys, null fields, empty emails, non-string evidence entries, and deliberate boundary fixtures. Store the prompt version, fixture identifier, raw response subject to privacy policy, parse verdict, latency, and evaluator model configuration. Never send real email, listing databases, or credentials through this test path. This evidence supports a limited decision. Whether a particular judge configuration can consistently classify unsupported listing claims on the validated fixture set. It cannot establish factual truth beyond the supplied records, current market data, legal compliance, fairness across populations, or superiority of one assistant variant without a paired comparison design and uncertainty reporting. The judge can also fail on negation, coreference, numeric transformations, mixed claims, multilingual text, adversarial formatting, or retrieval records whose schema is ambiguous. These failure conditions belong in the judge's model card and calibration results. For an AI engineer, this artifact is the daily interface between product behavior and measurable evidence. Evaluation engineers version prompts and boundary fixtures. ML platform engineers run the adapter and preserve artifacts. Product engineers consume typed verdicts and release gates, and safety engineers challenge the criterion with adversarial cases. Release Evaluator Suite v1 only after recording validation results and a model card for each learned judge, covering intended use, labels, evidence boundary, known failure modes, calibration set, and escalation policy. The narrow takeaway is to write one context-complete, machine-readable judge prompt for one decision, then validate the instrument before trusting its comparison. Known judge biases. The evaluator should be tested under controlled comparisons before its score becomes a release metric. Use responses with equal facts and policy compliance, but different lengths. Swap their order, match their length and content, and compare judge families. These checks can expose a preference for verbosity or another measurement artifact that could be mistaken for product improvement. Treat the judge as an instrument whose behavior must be characterized, not as a direct observer of quality. A judge does not observe quality directly. It applies a decision procedure to a prompt, two responses, and some context. Its output, therefore, has an error profile, as a retrieval test or classifier does. Bias includes not only an incorrect label, but also a systematic tendency to reward an irrelevant property. For the real estate assistant, the evaluator model card should include 4 diagnostics: position bias, verbosity bias, self-preference, and task-specific bias. Position bias is a preference for the response shown first or second, independent of its content. Verbosity bias is a preference for longer, more elaborately explained responses when length is not part of the criterion. Self-preference means giving elevated scores to responses produced by the judge's own model family, style, or instruction conventions. Task-specific bias is sensitivity to features that correlate with quality and calibration fixtures but are not part of the task, such as polished greetings, disclaimers, or a particular formatting style. These diagnostics do not prove that a judge is unusable. They identify conditions under which its score needs correction, stratification, or human review. They also turn the 6.4 judge contract into a testable artifact by holding the prompt, rubric, and adapter behavior fixed while changing one control property of the comparison. Reverse the pair to test whether the judge's verdict depends on which response appears first. For pairwise evaluation, submit the same 2 responses twice, once as A versus B, then as B versus A. Keep the rubric, buyer request, listing evidence, decoding settings, and other context fixed. If the verdict changes when only the positions change, the disagreement is evidence of position sensitivity. A production comparison should either aggregate both orders or exclude and separately report unresolved reversals according to a documented rule. The buyer email fixture makes the test concrete. Email A says, the buyer is interested in the 2-bedroom property and asks whether Saturday's viewing is available. Email B says the same thing in a longer form, adding courteous framing, but no new fact. If the judge selects A in one order and B in the reverse order, neither answer has demonstrated superiority. The evaluator has exposed instability. The position swap must be a paired operation, not a second independently sampled test. A new random seed, change context, or altered whitespace can introduce additional variation and make the diagnosis ambiguous. Preserve both raw prompts and parse verdicts so a reversal can be inspected. Measure length instead of automatically rewarding it. Length is sometimes a requirement. A disclosure may need specific content, and a tool use trace may need enough detail for audit. But when the criterion is factual completeness or faithful response to a buyer, extra words are not automatically quality. Analyze response length as a possible confounder. Create length slices from a collection of matched examples. Concise and verbose responses with equivalent facts, short and long responses with the same error, and responses whose length varies without changing the required action. Each fixture should carry a stable slice label, a semantic equivalence or error label, and any task-relevant facts that human adjudicators used. Report judge preference within each slice rather than relying only on the aggregate win rate. A judge that favors verbose answers overall may behave appropriately when verbosity is explicitly required and inappropriately when it is irrelevant. A longer response is not evidence of verbosity bias when a shorter response omits a task-relevant fact, such as the requested viewing date. Length diagnostics therefore require semantic matching or human-checked fixture labels rather than character counts alone, and must report equivalent pairs separately from boundary cases. The diagnostic uses the shared evaluator contract. The established fixture and judgment schemas from real_state_eval.shared and the credential-free evaluator adapter from real_state_sandbox. The fallback is only a test double for a clean checkout or isolated documentation run. And production must use the shared adapter rather than redefine a competing application schema. The code implements position and length diagnostics over paired fixtures. For each fixture, it obtains a forward judgment, obtains a reverse judgment, normalizes that reversed result into the original fixture frame, records both response lengths and judgments, and aggregates reversals, position wins, ties, and verbose wins by slice. The example defines an equivalent pair and a required content boundary case, runs the diagnostics with a deterministic length test double, asserts the expected slice results, and prints the report. The test double is documentation and sandbox only. The production path uses the shared adapter. For the equivalent slice, the fallback reports one fixture, 0 position reversals, and one verbose win because the mock rewards length when the facts are equivalent. The required content slice also has a verbose win, but it is a boundary case because the concise response omits the requested viewing date. The assertions make both distinctions executable. The shared fixture loader should provide a larger human check collection, and the sandbox adapter should replace the test double without changing run and record diagnostics or the report contract. A real report should preserve fixture identifiers, judge configuration, raw prompts, parsed verdicts, token or character lengths, slice labels, equivalence and error labels, and the adjudication source. Aggregate results separately by slice and judge configuration. Pin dependencies and run automated tests in the companion repository. Do not connect this diagnostic to real email, listings, credentials, or other consequential tools. Challenge the judge's family resemblance. Run the same fixture suite through at least one judge from the generator's model family and one from a different family, while keeping the rubric and response order protocol fixed. Agreement across families is useful evidence, but not proof of correctness. Disagreement can indicate self-preference, rubric ambiguity, or a genuine task boundary. Where possible, also compare against non-LLM checks, such as required field validation, citation presence, exact numerical checks, or a human-labeled slice. Do not treat a judge's rationale as proof of correctness or as observable private reasoning. Preserve it only as an explanatory artifact subject to review, and base the metric on the declared verdict and externally checkable evidence. The code artifact is intentionally limited to position and length diagnostics. Cross-family runs belong in the same evaluator suite report and should preserve the same fixture and raw artifact contract. When uncertainty remains, repeat judgments rather than merely expanding the sample. Repeat judgments for ambiguous cases. Repeat both pair orders, and where the provider permits control variation, repeat with documented seeds or sampling settings. Record agreement rates, reversals, ties, and escalations. A stable verdict on an easy fixture says little about boundary cases, while a noisy verdict on a difficult fixture should reduce its influence on an automated gate. If independent runs alternate between verbose wins and tie, do not select the majority without qualification. Mark the case ambiguous. Inspect whether the rubric specifies a length preference, and route representative examples to human review. When concise communication is required, encode that requirement explicitly rather than relying on the judge to infer it. Update the evaluator suite with bias fixtures, position swap and length slice reports, cross-family judge results, and a model card covering intended use, known sensitivities, escalation rules, and evidence boundaries. Preserve compatibility through the shared fixture schemas and sandbox adapter, then separate development from validation fixtures without turning diagnostics into tuning data. Use these tests only to assess whether a judge configuration is stable and task-aligned for the tested comparison and fixture distribution. They cannot establish real-world factual correctness, fairness across populations, legal compliance, or superiority on untested languages, formats, domains, or user intents. They may fail when equivalence is mislabeled, distinctions are hidden in wording, context is incomplete, or model and prompt changes alter behavior. Release Evaluator Suite v1 only with these limitations, validation results, and a separate model card for each judge. Treat every judge as a calibrated instrument. Evaluation engineers maintain counterexamples and adjudication rules. Product engineers prevent irrelevant style preferences from becoming acceptance criteria. ML platform engineers preserve paired artifacts and reproducible configurations. And safety engineers probe task-specific blind spots. Swap positions, analyze length by validated slice, cross-check model families, repeat ambiguous decisions, and change the evaluator artifact when evidence reveals a bias. Calibration data must be separated before changing the judge prompt. Split the 180 labeled emails before changing the judge prompt. An illustrative allocation uses 108 for judge design, 36 for development checks, and 36 for the final test, preserving class proportions as far as the counts allow. This is not a universal recommendation. A judge that improves on the 108 examples may still fail on the 36 examples it never influenced. Without separation, improvement may reflect memorization of the calibration set rather than a more trustworthy measurement instrument. Protected set sizes depend on label prevalence, the number and importance of slices, the uncertainty a release decision must tolerate, and available adjudication capacity. Rare or consequential categories need enough protected examples for meaningful decisions. Otherwise, report them as diagnostic rather than conclusive. High-risk releases, many-slice comparisons, or narrow uncertainty targets call for a larger protective validation set and an untouched test set. A small development set can catch obvious failures during early prompt iteration, but it cannot support a precise final claim. Development and validation serve different purposes. Judge development may include prompt wording, rubric refinement, label definitions, few-shot examples, model selection, threshold choices, and decisions about special handling for failures. Those choices may learn from evidence in the development partition. The test partition is a sealed decision surface used only after the judge configuration is frozen. This separation applies even when the judge is an LLM rather than a trained classifier. An inspected example can influence a prompt edit, and a discussed disagreement can become an implicit rule. After repeated inspection, a test result is no longer a clean estimate on unseen cases. Restrict test access, version its membership, and record an owner. The release report should state when the test was opened, which configuration was evaluated, and whether any test item caused a later change. If the judge changes afterward, that test is development evidence for the new version, not final validation. In the real estate assistant example, the illustrative 108 email judge design partition can test whether the rubric distinguishes useful property answers from fluent but unsupported ones. A 36 email development partition can check prompt revisions and known bias fixtures, while the remaining 36 emails are reserved for the frozen evaluator suite. Other projects should change these numbers after reviewing prevalence, slice coverage, uncertainty targets, and adjudication capacity. The repository artifact should include the split, dataset version, rubric version, judge configuration, and access log. Reliable calibration begins with defensible reference labels. A judge cannot be calibrated more precisely than its reference labels allow. Trusted labels need an explicit contract covering the question being scored, allowed labels, evidence available to the annotator, and the escalation path for ambiguity. In the email suite, correctness may require both a faithful answer and appropriate uncertainty when listing context is incomplete. Fluent prose does not excuse inventing a fee, school assignment, or transaction rule. Use adjudicated labels when decisions are consequential or difficult. Preserve the original label, corrected label, reason for correction, reviewer or review role, and correction date. Do not silently overwrite values. Correction logs can expose an underspecified rubric, missing annotator context, or an apparently objective category that contains several decisions. Those findings should change the label contract or fixture design, not merely the score. Preserve trusted labels without treating rare categories as statistically stable. Stratification can place relevant classes in each partition, but it cannot manufacture examples. If only 2 emails concern an escalation rule, placing one in development and one in test does not validate that rule broadly. Identify sparse classes and treat their results as diagnostic rather than conclusive. This section addresses how to make the partitions representative and difficult. Random sampling alone can produce an easy test. Include ordinary traffic patterns and cases most likely to expose evaluator failure, including terse requests, long forwarded threads, conflicting listing fields, missing context, ambiguous intent, negation, near duplicate emails, and answers that are correct but less verbose. Difficult cases should supplement representative cases because an all-trap test measures trap resistance rather than normal usefulness. Keep related items together when they share a source, conversation, template, listing, or synthetic generation seed. Otherwise, a near duplicate can place the answer pattern in Judge design and its lightly edited twin in test. Group-aware splitting usually reduces the apparent amount of independent evidence, which makes the result more honest. An email asking whether a property is near transit may be answerable from a supplied listing description, while an email asking whether a tenant is legally entitled to a particular accommodation requires domain-specific policy and possibly qualified human review. Both may look like factuality tasks, but the same Judge rubric should not be assumed valid for them. A successful score on listing-grounded answers cannot establish competence on legal or fair housing decisions. The next principle is to prevent few-shot leakage. Few-shot examples are training data for the judge's behavior when they appear inside a prompt. They can shape observed behavior, but they do not literally retrain the model's parameters. Keep every test item, paraphrase, quoted answer, distinctive identifier, and label rationale from the held-out partition out of the judge prompt, rubric examples, developer documentation used during prompting, and automated regression fixtures. Retrieval can also leak information, so a judge's reference bank needs the same partition controls as the primary dataset. Run exact and normalized duplicate checks first. Normalize case and whitespace. Hash stable record identifiers and compare text fingerprints. Do not mistake these checks for semantic leakage detection. Then inspect clusters of near duplicates, shared templates, and repeated listing facts. Store the leakage check report with the split manifest. If a test item leaks, quarantine it, document the reason, and either replace it from an untouched reserve or report the reduced test scope. Do not quietly move it into development while preserving the old result as if nothing changed. For the 180 emails, the split script creates a deterministic manifest using a recorded seed, groups related messages before allocation, checks that identifiers are disjoint, rejects duplicate normalized content across partitions, and compares per label counts with documented tolerances. The evaluator repository records a versioned split manifest, a label correction log, and the judge model cards validation section. The prompt template and calibration notebook reference those artifacts rather than embedding an untracked list of examples. A reproducible split artifact. The Python artifact uses the shared email record contract and fixture loader. It computes jointly consistent per label targets, preserves related groups, checks normalized duplicates and disjoint identifiers, and fails diagnostically when a requested tolerance is infeasible. Its allocation method must scale to the illustrative 180 record fixture rather than enumerate every assignment. Repository tests should verify completion, requested sizes, label tolerances, group integrity, disjoint identifiers, and manifest generation. Provider-specific adapters remain outside the durable core example, and the fixture loader uses synthetic records without external credentials or consequential side effects. The manifest should record the seed, dataset version, partition sizes, per label targets and observations, group policy, tolerance, leakage check result, and correction log version. If group constraints prevent exact rounded targets, the function must report the targets, observed counts, group sizes, and best achievable allocation. The release owner may choose an untouched reserve, revise partition sizes, or approve a non-zero tolerance in a manifest. That approval is a data decision, not a reason to silently accept a non-representative split. For the illustrative 180 email setup, use 108, 36, and 36 only if those counts provide adequate slice coverage and uncertainty for the intended release decision. If they do not, enlarge the protected validation or test partition, reduce the scope of the claim, or collect more adjudicated data. Run the repository-level test in a clean pinned environment. Its exact output belongs to that run rather than being inferred from a smaller excerpt. This artifact supports a narrow decision. Whether the frozen judge configuration behaves acceptably on the specified, held-out email distribution under the stated labels and leakage controls. It cannot prove correctness in the world, fairness across populations, legal compliance, robustness to new languages or workflows, or superiority on untested intents. It can fail when labels are wrong, context is missing, near duplicates escape detection, sparse categories dominate interpretation, or the judge's underlying model changes. Exact stratification does not fix sampling bias, and a group-preserving split does not establish independence between all external sources. Maintaining this boundary is daily platform work as much as evaluation work. Preserve manifests in CI. Expose correction history to reviewers. Keep consequential cases in a human review lane, and prevent product prompts from consuming test fixtures. Release Evaluator Suite v1 only when it's split, corrections, leakage report, validation results, and judge model card travel together. Develop the judge on visible evidence. Validate it on protected evidence. And choose split sizes from prevalence, coverage, uncertainty, and adjudication requirements rather than a fixed recipe. Confusion matrices, TPR, and TNR. The judge reports that the new real estate assistant is safer because its score improved, but it more often marks longer answers as supported, including answers containing an ungrounded sentence. A release decision based only on that aggregate score could therefore increase unsupported claims while appearing to reduce them. Protected reference labels and judge outputs from the held-out calibration workflow are cross-tabulated to measure false positives and false negatives. The evaluator is a measurement instrument, not an oracle. Its errors can be asymmetric. It may miss unsupported claims more often than it falsely flags supported claims, or the reverse. Calibration therefore requires a confusion matrix, explicit costs, and slice-level results rather than one headline accuracy number. Before calculating the confusion matrix, name the positive class. The chosen positive class determines how predictions and errors are interpreted. Let y equal 1 when the protected reference label says the response contains an unsupported claim, and let y equal 1 when the judge flags it. The judge's positive prediction is a flag. The positive reference label means human review using the frozen rubric and available source context found at least one unsupported claim. Choosing a different positive class, such as fully supported, would change the names and interpretations of the predictions and the error estimates passed to the correction method. The confusion matrix entries are determined by comparing the judge's binary decision with the protected reference label for each held-out response. A true positive occurs when the reference label identifies an unsupported claim and the judge flags the response. Y equals 1 and Y equals 1. A false positive occurs when the response is supported, but the judge flags it. Y equals 0 and Y equals 1. A true negative occurs when the response is supported and the judge passes it. Y equals 0 and Y equals 0. A false negative occurs when the response contains an unsupported claim, represented by Y equals 1, but the judge passes it, represented by Y equals 0. The unsupported claim case returns us to the central failure. A verbose answer can include one unsupported statement while surrounding it with accurate material. If the judge's prompt or threshold implicitly treats mostly useful as negative, it creates false negatives precisely where the evaluator is supposed to provide a safety signal. Now calculate each rate rather than relying on the raw count. Use these 4 symbols for the cell counts. The following principal rates assume non-zero denominators. TNR equals \frac TN plus FP. TPR, or sensitivity, is the proportion of genuinely unsupported responses that the judge flags. TNR, or specificity, is the proportion of supported responses that the judge leaves unflagged. Balanced accuracy gives equal weight to the positive and negative classes. Prevalence is the observed proportion of unsupported responses in the validation sample. Observed success means the judge agrees with the reference label. Observed success is the number of true positives plus true negatives divided by the total number of true positives, true negatives, false positives, and false negatives. These quantities describe different properties. Observed success can be high when unsupported claims are rare, even when TPR is poor. A judge that flags nearly everything can have high TPR but poor TNR. Balanced accuracy reduces the influence of class prevalence when comparing the two class conditional rates, but it does not replace inspection of the individual rates, label quality, dependence, or uncertainty, especially in small slices. The frozen validation set contains 200 responses, 40 with unsupported claims and 160 without. The judge catches 34 unsupported responses and incorrectly flags 16 supported responses. So TP is 34, FN is 6, FP is 16, and TN is 144. TPR is 0.85, TNR is 0.90, balanced accuracy is 0.875, prevalence is 0.20, and observed success is 0.89. The judge is useful but not a perfect labeler. 6 unsupported responses passed, and 16 supported responses entered unnecessary review. The companion artifact computes these values for the overall set and each declared slice. It consumes the shared evaluation record rather than inventing a second row contract. The provider-specific judge adapter belongs upstream and must produce the normalized Boolean fields reference underscore unsupported and predicted underscore unsupported. This code computes confusion counts and reports TPR, TNR, balanced accuracy, prevalence, and observed success for the overall validation set and for each intent slice. The expected overall values are TPR 0.85, TNR 0.90, balanced underscore accuracy 0.875, prevalence 0.20, and observed underscore success 0.89. Slice output depends on the shared fixture, but a real fixture must list every declared slice, its denominator, and any minimum count warning. The implementation uses no external service or credential. It consumes the shared schema and fixture established earlier, validates required fields and exact Boolean types, rejects missing or malformed records, and should run in the pinned test environment with the lock file and fixture version recorded. Choose the threshold for the decision you actually make. Depending on the judge implementation, an LLM-Judge may produce a score or probability-like signal before a binary flag. Choose the threshold using the costs of false negatives and false positives and the capacity of the downstream workflow, not merely observe calibration success. Evaluate thresholds on a held-out calibration split and select the threshold that minimizes the specified cost. The cost at threshold T is defined as \operator name cost T equals C_FN /FN T plus C_FP /FPT. C_FN and C_FP are documented decision weights for one false negative and one false positive, not probabilities or universal dollar values. FN T and FPT are the corresponding counts. For a safety floor, first retain thresholds with TPR T greater than or equal to 0.90, then minimize cost among them. If review capacity binds, add and record a maximum review volume constraint such as FPT less than or equal to 20. For unsupported claims and property advice, a false negative may allow an ungrounded statement into a user-facing answer, while a false positive may consume human review capacity, delay responses, or suppress a useful answer. A pre-release safety gate may accept more false positives to reduce false negatives. A high-volume monitoring alert may require a higher TNR to avoid flooding reviewers. This makes the trade-off auditable. If a validation sample contains no unsupported responses, TPR is undefined, not zero. If it contains only unsupported responses, TNR is undefined. The judge cannot demonstrate a class-specific capability that the sample never tests. A threshold tuned for a rare, unsupported claim rate may behave differently when a new retrieval source, language, or workflow changes prevalence. Inspect slices before accepting the aggregate. Compute the same confusion matrix by intent, language, answer length, retrieval status, property type, and other factors that could change judge behavior. Compare denominators as well as rates. A slice with two unsupported examples and a TPR of 1.00 is not equivalent evidence to a slice with 200 examples and the same rate. Review underlying disagreements, especially false negatives, rather than treating the judge's rationale as proof of correctness or as observable private reasoning. For the cumulative real estate assistant, Evaluator Suite V1 includes a threshold manifest, confusion matrix report, slice definitions, minimum count warnings, disagreement links, and a judge model card. The model card records the positive class, reference label procedure, validation split, threshold, TPR, TNR, balanced accuracy, prevalence, observed success, known failure modes, and intended use. Because human reference labels may involve disagreement and context-dependent uncertainty, preserve adjudication notes or label review status. Point metrics alone do not express that uncertainty. The release claim is narrow. Under the held-out distribution and rubric, the judge provides a measured signal suitable for the specified review or gate. It does not establish factual correctness in every market, language, or future retrieval condition, or justify a consequential housing decision by itself. Evaluation and AI engineers maintain label contracts, run slice reports in CI, investigate denominator changes, and tie judge versions to their validation evidence. ML platform and product engineers preserve manifests and route alerts to sandboxed review workflows. Safety engineers use the error profile to set escalation policy. Confusion matrix rates assume that the reference label process is sufficiently defined for the intended decision, that the held-out sample represents deployment conditions closely enough to be informative, and that each row's binary decision is valid. dependence among responses, label noise, small slices, prevalent shift, threshold overfitting, and changes in retrieval or rubric can make point estimates misleading. The evidence can support a documented evaluator threshold, review gate, or monitoring policy under the stated conditions. It cannot prove factual correctness everywhere, that a judge's rationale is true, or that a housing-related outcome is safe or lawful without separate domain review. A judge's score becomes decision-relevant when the team knows what positive means, how the cost rule selected the threshold, how often each kind of mistake occurs, where those rates change, and which action the evidence can and cannot support. Correcting imperfect judge estimates is the next requirement before treating an observed judge positive rate as a supported answer rate. A sampled set of production emails can make the real estate assistant appear to have improved when the judge has merely learned to reward longer answers. Do not ship the observed judge positive rate as the system supported answer rate. First, estimate how the judge behaves on known labels, then correct the rate or report that the evidence is insufficient to correct it. The analysis distinguishes two sources of uncertainty. Suppose the assistant receives a random sample of production emails, and an automated judge classifies each response as supported or unsupported. There are two different problems in that statement. A false positive occurs when the judge marks an unsupported answer as supported. A false negative occurs when it misses an answer that is genuinely supported. Sensitivity measures positive judgments among truly supported answers, while specificity measures negative judgments among truly unsupported answers. The sampled emails are only one possible sample from the production population, so the measured rate can vary even with a perfect judge. Larger samples generally narrow this uncertainty, but they do not fix systematic judge bias. The implementation assumes independent cases. When emails share a thread, user, property, or account, the cluster must be the sampling unit or the interval may be too narrow. The production sample records the observed judge outcome. The judge model card records sensitivity and specificity estimates from a labeled validation set. The statistical report records the interval produced by resampling production cases. A single unqualified percentage conceals which uncertainty is being managed. Correcting an observed rate. Let. The quantity P represents the actual population rate of answers that are supported. The quantity Q is the proportion observed after the judge labels answers as supported. The quantity S is judge sensitivity, the probability that the judge returns a positive result when the answer is truly supported. Let C be judge specificity, $P, J, caret, / mid T caret $, the probability of a judge negative result given negative truth. Partition judge positive outcomes according to the unknown truth. The observed judge positive rate is $Q equals SP plus 1C, 1P $. The first term is the correctly detected supported answer proportion. The second is the false positive proportion among unsupported answers. Solving for $P gives the corrected supported proportion. The corrected estimate is $P equals / frac Q plus C, 1S plus C, $1. Use the correction only when $S plus C, 1 / NE $0. The denominator is the judge's Uden index, measuring separation from random classification under this binary formulation. The implementation requires a positive Uden index. 0 is uninformative, and a negative value indicates an inverted classifier whose labels would need to be deliberately reversed and recalibrated before using the correction. When the denominator is near 0, a small calibration error can cause a large change in the corrected estimate. If the numerator or corrected result falls outside $1, do not clip silently. The observed rate and assumed calibration may be incompatible, or the calibration estimates may be too uncertain. Suppose the production sample has $Q equals $0.78, while held-out reference labels estimate sensitivity $S equals $0.90 and specificity $C equals $0.80. Substitution yields $P equals \frac 0.78 plus 0.80-0.90 plus 0.80-1 equals \frac 0.5 0.70 approximate $0.829. A 78% judge positive rate can correspond to an estimated supported answer rate of about 83% when false negatives outweigh false positives at the assumed operating point. This remains an estimate, not hidden truth, and it does not establish factual correctness, housing policy compliance, or safety in a consequential transaction. The rate correction is usable only if its calibration assumptions carry from validation into the production sample. The correction is identifiable only under explicit assumptions. The production sample must represent the reported population, or its sampling design must be accounted for. Reference labels must be sufficiently reliable and use the same support rubric. The judge threshold, prompt, model configuration, input fields, retrieval context, language mix, and important slices must match, or their differences must be measured. Most importantly, sensitivity and specificity must transfer approximately from validation to production. Calibration can fail when validation uses short English answers about listing facts, but production contains long email threads involving zoning, financing, missing citations, or multiple retrieved listings. A single global confusion matrix can hide that drift. Validate by property type, market, answer length, retrieval availability, conversation turn, and policy-sensitive category. If transfer fails, do not manufacture a corrected rate. Collect labels in the target slice, recalibrate the judge, or report an interval over plausible calibration values. The durable artifact joins every sample production case to its sampling metadata, sampling unit, judge version and threshold, observed outcome, reference label status when available, and calibration manifest. The evaluator suite should report the corrected estimate beside the uncorrected rate, validation counts, slice coverage, and warnings about extrapolation. Uncertainty assessment should address both the production sample and the calibration values used in the correction. Repeatedly resample the production cases with replacement and recompute the statistic. For each replicate, calculate the observed judge-positive rate and apply the correction using the selected sensitivity and specificity. Percentile endpoints of the corrected estimates provide a practical conditional interval when the sample is representative and the declared sampling units are independent. For clustered email data, resample threads, users, properties, or another defensible primary unit rather than individual messages. The interval is conditional on the supplied calibration values unless calibration uncertainty is also propagated. Even then, report that it is not automatically a fully calibrated confidence guarantee, especially for small samples, dependent cases, or a change production mix. Sensitivity analysis is the minimum protection against false precision. Recalculate across a plausible sensitivity and specificity grid, preferably informed by slice-level validation uncertainty. Before use, verify that each range satisfies 0, less than or equal to low, less than or equal to high, less than or equal to 1. Every combination has a positive, non-negligible Uden index, and every corrected estimate lies in 0. If a combination is non-identifiable or incompatible, return a warning and no bound rather than dropping or clipping it. If a valid grid changes the release decision, the evidence supports more labeling, a narrower claim, or human review, not a confident gate. With sensitivity and specificity both at 0.60, S plus C minus 1 is 0.20, and the correction is unstable. At 0.50 for both, the denominator is 0, so the observed positive rate provides no identifiable information about the true rate under this model. When both values are below 0.50, the judge is inverted rather than a usable validated instrument for this correction. Bootstrap resampling cannot repair an uninformative instrument. If production emails are oversampled from escalations, a raw population rate is wrong unless sampling weights or a representative sampling plan are used. The companion artifact changes Evaluator Suite v1 by adding a bias correction report, conditional and calibration inclusive interval labels, sensitivity bounds, and sampling unit metadata. It also adds a release warning when calibration transfer or population representativeness is unverified. The judge model card should link to this report rather than treating its validation confusion matrix as a permanent property of the judge. Next, the implementation is provided. The implementation uses standard Python only. It expects the production sampler to provide one Boolean judge outcome per independent sampled case. It does not send email, call a provider, or access a database. The deterministic seed makes the artifact reproducible for tests and review. For clustered sampling, provide one observation per cluster or replace the resampling unit with a cluster bootstrap before using the interval. This code defines a validated correction, a reproducible bootstrap interval, sensitivity bounds, and tests for invalid inputs and non-identifiable calibration. Correction validates the observed rate, sensitivity, and specificity, computes the denominator as the Uden index, and rejects non-positive separation or an estimate outside 0 to 1. Bootstrap interval requires production cases, validates the calibration, resamples Boolean outcomes with a seeded random generator, computes corrected estimates for the requested replicates, and returns index confidence limits. Sensitivity underscore bounds validates both ranges, evaluates every endpoint combination, and raises an error if the region is not fully estimable rather than silently omitting a corner. Run underscore test checks valid correction, empty input, invalid probabilities, non-positive Uden index, incompatible correction, deterministic bootstrap output, reversed ranges, and a non-identifiable range. The main block runs the tests, computes the corrected estimate, bootstrap interval, and sensitivity bounds, then prints the results. With Python 3.11 and the standard library, the declared seed and 2000 replicates produce output of the stated form. The report indicates that tests passed. The observed rate is 0.780. The corrected estimate is 0.829. The bootstrap 95% interval is 0.714 to 0.929, and the sensitivity bounds are 0.797 to 0.859. The point estimate conditions on sensitivity of 0.90 and specificity of 0.80. The bootstrap interval captures variation across 100 independent production cases while holding those calibration values fixed. So, it is not a calibration-inclusive confidence guarantee. Sensitivity bounds evaluate the four corners of the validated rectangle, with sensitivity from 0.88 to 0.92 and specificity from 0.77 to 0.83. The function validates that rectangle and refuses to report bounds if any corner is non-identifiable or yields an impossible corrected rate. Because this fractional linear correction has positive denominator, its extrema over the rectangle occur at a boundary corner, making the four-corner calculation sufficient after validation. If calibration uncertainty is not plausibly rectangular, use a justified region or joint calibration resampling. The tests cover empty production input, invalid probabilities, zero or negative Uden indices, incompatible corrections, reproducibility, and invalid or non-identifiable sensitivity ranges. Production hardening should also include validation record resampling, finite population or sampling weight support when needed, slice-level reports, minimum count warnings, dependency lock files, and test for clustered bootstrap units. Provider-specific judge adapters should remain outside the durable statistical core. The method fails when labels are not meaningful, when the sample is biased and unmodeled, when judge errors depend strongly on unmeasured case features, or when the judge changes without recalibration. It also cannot determine whether an answer is legally appropriate or whether a user should act on it. It can support a bounded comparison with a pre-declared threshold, such as deciding whether to send a sampled cohort for additional human review or pause an evaluator release. It cannot support an unconditional claim that the assistant is correct across all markets and users. For AI, evaluation, and ML platform engineers, the work is to maintain calibration manifests, make reports reproducible, expose denominator, sampling unit, and slice warnings, and keep evaluator versions tied to evidence. Product and safety engineers use the bounds to choose rollout or escalation policies, not to turn a noisy score into a guarantee. Estimate the system rate only after separating judge error from sampling error, stating the transfer and sampling unit assumptions, and showing how the conclusion changes under plausible calibration. Evaluator Suite V1 should include the corrected estimate, its conditional bootstrap interval sensitivity bounds, sampling metadata, and a judge model card that makes the evidence and its limits visible. This section examines how to compare variance fairly. Prompt A and Prompt B are run on the identical buyer requests, and B receives the higher average judge score. But B also produces longer answers, and the judge rewards the extra explanation even when the recommendation is unchanged. If variants use different samples or only averages are reported, the team cannot distinguish an assistant improvement from case mix or a length preference. A variant decision therefore requires case-level pairs, an effect size, and uncertainty around that effect. Use each case as the match unit for the comparison. Freeze the evaluation set before comparing variants. Each record needs a stable case identifier, the buyer request and permitted context, expected behavior or reference facts, and any analysis slice labels. Run both variants on every eligible case with the same retrieval snapshot, tool sandbox, timeout policy, and evaluator version where possible. Preserve raw outputs because scores alone cannot explain a surprising result. In the buyer 017 example, a completeness-favoring judge can score prompt B higher even when its additional paragraph introduces unsupported or potentially sensitive inferences. The evaluator's error profile is therefore part of the comparison. A judge rationale is evidence about the judge's classification process, not proof that the answer is correct. The primary observation is a pair, not two unrelated observations. For case I, S_AI is the score for variant A, and S_by is the score for variant B on that same case. Define the pair difference as B's score minus A's score for case I. B_I equals S_I. A positive value means B scored higher on that case. A negative value means B scored lower. Within cases, estimate the improvement by taking the mean of the paired differences. The estimated improvement is the mean paired difference \hat \delta equals \frac \__ equal Here, N is the number of complete, valid pairs. D_I is B's case-level change relative to A, and the estimated improvement is an absolute change in score units. If a score is 0.70 and B scores 0.76 on average over the same cases, the estimate is 0.06 or 6 percentage points when scores are proportions. This is an absolute difference, not a claim that B is 6% better in every practical sense. Pairing removes one major source of noise because a difficult request affects both variants, so its baseline difficulty is differenced out rather than appearing as unexplained variation between two samples. Independent sample methods discard that structure and can produce wider intervals or, when the samples differ in composition, a misleading apparent improvement. Estimate uncertainty around the difference rather than reporting only a point estimate. A point estimate is incomplete without an interval. For independent case-level pairs, risk-sample the observed pairs with replacement, or equivalently risk-sample the paired differences, preserving the relationship between A and B within each case. Recompute the estimated difference for every risk sample, then form the interval from the chosen lower and upper bootstrap quantiles. This baseline is conditional, not universal. It assumes that case-level pairs are the sampling units and are sufficiently independent. For clustered cases, risk-sample the cluster rather than individual rows and use a cluster-aware bootstrap or another suitable method. For very small samples, highly skewed differences or bounded scores, consider a bias-corrected and accelerated bootstrap, a paired permutation test, or a paired sign or sign rank method when a mean is not the appropriate estimate. State the method and its assumptions in the report. The cases should represent the population to which the team intends to generalize. Pairs should be complete or handled under a declared missingness rule, and dependence should not be ignored. A bootstrap interval does not repair a biased evaluation set, an unstable judge, or leakage between development and decision data. The companion repository artifact is a durable statistical core that uses no provider credentials or consequential tools, except deterministic score arrays produced by shared score adapters, and emits a decision table. Its repository entry point converts earlier shared evaluation records into those arrays without redefining the established case schema. This function validates that the paired score arrays have the same non-zero length, that the bootstrap settings are valid, that the minimum improvement lies in its allowed range, and that all scores are finite proportions. It computes B-A differences in their observed mean, repeatedly risk samples those differences with a seeded random generator, sorts the bootstrap means, and selects the lower and upper bootstrap quantiles. It labels the result a release candidate when a lower bound reaches the minimum improvement. Otherwise, it holds the result for review. The report formatter returns the comparison fields as a decision table row. The repository entry point uses the shared records and score adapters from the preceding evaluation chapters. These are repository interfaces, not replacement toy schemas. They keep case identity and metadata attached until the comparison is complete. This entry point loads shared evaluation records, groups them by case and variant, retains only cases containing both A and B, and sorts the pairs by case identity. It scores each variant through the shared adapter, passes the paired score arrays to the bootstrap with a 0.03 minimum improvement, and formats the resulting decision report. The key choice is to resample differences between paired cases, not A and B independently. The production adapter sorts and joins records by stable case_ID, so change file order cannot silently create false pairs. Clustered production data require a cluster-aware adapter instead of this row-level function, and the report should identify the cluster as the resampling unit. The test module covers deterministic reproducibility, paired resampling behavior, invalid inputs, mismatched lengths, and the threshold decision. Its fixture uses two variants whose case-level differences are either 0.00 or 0.10. Independently resampling the variants could manufacture combinations that never occurred on a real buyer request. This test module checks reproducibility, paired resampling, input validation, and threshold control decisions. This percentile index implementation is a simple order statistic interval and a baseline for independent case-level pairs, not a universally preferred confidence interval method. It may be unsuitable for small samples, highly skewed differences, bounded scores, or dependent observations. In those settings, change the resampling unit or use a method justified by the evaluation design. Name that method in the statistical report and rerun the artifact in the pinned companion repository environment before publishing exact output or test counts. Now choose the test and control how broadly you search. Use a paired bootstrap when the score difference is the quantity of interest and the sampling design is clear. A paired permutation test can test a sharp no difference hypothesis by randomly swapping A and B within each pair. A paired signed rank or paired sign test may be preferable when scores are ordinal or distributional assumptions make a mean inappropriate. Select the test from the data contract, not after inspecting favorable results. Report the test, resampling unit, number of resamples or permutations, seed where deterministic reproduction matters, and missing data rule. Trying many prompts, judges, slices, thresholds, and bootstrap settings can make one apparently favorable interval arise through selection. Pre-declare the primary metric, comparison, evaluation set, and minimum worthwhile improvement. Distinguish exploratory analyses from confirmatory decisions, and correct for multiplicity when making several formal claims. Depending on the decision, a conservative Bonferroni adjustment, false discovery rate control, or a hierarchical analysis may be appropriate. At minimum, preserve the complete experiment ledger so discarded trials remain visible rather than silently replaced by the winner. For the real estate assistant, the decision table should state whether prompt B's paired improvement clears the pre-declared threshold, show the absolute difference and interval, and break out relevant slices such as buyer intent or retrieval availability. If B wins overall but loses on requests involving missing listing facts, the release decision may be a targeted hold rather than a global launch. The evaluator suite should gain paired run records, bootstrap configuration, multiplicity policy, slice warnings, stable case IDs, score, judge versions, and a model card entry describing the judge's length sensitivity and validation boundaries. It can then be released as version 1 with its validation results instead of publishing an unsupported B is better label. Pairing is invalid when variants are evaluated on different cases, even if their averages are comparable. When both variants process one unusually long conversation, the effective sample may be one conversation rather than its many turns, so the uncertainty estimate must match the decision unit. The comparison can support a bounded choice between variants under a stated evaluator and a sampling design. It cannot establish universal correctness, legal or fair housing appropriateness, robustness to future distributions, or superiority across repeated stochastic executions. It also cannot compensate for an uncalibrated judge. Operationally, compare variance on the same cases, compute case-level differences, report the absolute effect with an appropriate confidence interval, and account for experiments searched. Use a simple paired percentile bootstrap only when independent case-level assumptions fit. Otherwise, use cluster-aware resampling or another paired method. This section focuses on stochastic reliability. Run each tool using task 5 times. One successful trace does not establish a reliable workflow. The assistant may find the correct listing, use the correct sandbox tool, and draft a compliant answer once, then select differently or omit a required constraint on another run. A paired comparison may therefore still be unsafe to release. Difficulty is not instability. A difficult task can fail consistently because its constraints are impossible or its fixture is intentionally sparse. That is item difficulty. Instability occurs when the same task alternates between valid and invalid behavior, such as filtering listings correctly on one run, calling the calendar tool too early on another, and omitting the required tool call on a third. For each task, record the number of successful runs rather than only whether it succeeded once. A run-by-item table shows whether failures cluster on difficult tasks or whether ordinary tasks are unreliable. Preserve the task identifier, fixture snapshot, tool schema, and pass/fail rubric for every repetition. Changing a fixture or tool contract creates a different experiment. The judge is part of the measurement instrument. If an LLM-judge rewards longer answers, repeated trials can reveal apparent improvement that is really verbosity or judge preference. A judge rationale records the judge's assessment. It does not prove correctness or access to private reasoning. For consequential slices, pair automated judgments with deterministic checks and human review. Retries require distinguishing two probabilities and the different release questions they answer. Let P be the probability that one execution passes under a fixed task distribution, and assume, for this calculation, that executions are independent and identically distributed. The probability that at least one of K attempt passes is given next. The probability of at least one pass in K attempts is 1 minus the probability that all K attempts fail, 1 minus P, raised to the kth power. The probability that all K attempts pass is given next. The probability that all K attempt pass is P raised to the kth power. Pass at least once is useful when a retry mechanism can safely discard failed attempts and retry without side effects. Pass every run is closer to the requirement for a workflow that sends a message, books an appointment, changes a record, or makes a recommendation without a reliable recovery path. These formulas are not guarantees. Independence may fail because the model, prompt, retrieval corpus, or tool fixture creates correlated behavior. Report the observed results alongside the assumption rather than presenting the calculation as a confidence interval. With one-run success probability P equal to 0.8 and 5 attempts, independents give a 0.99968 probability that at least one attempt succeeds, while all 5 succeed with probability 0.32768. A retry-oriented product might value the first number. An autonomous scheduling workflow should be alarmed by the second. The same one-run score supports sharply different decisions depending on the failure policy. The 5-run real estate trial. Run each tool-using task 5 times in the established sandbox. Record the task ID, run ID, available seed or provider settings, tool call trace, final response, deterministic rubric results, judge result, latency, and token or cost accounting. A compact local harness can summarize the core quantities without contacting a provider. This code defines trial records, validates repetition data, summarizes pass rates and variance, totals cost, and runs each task for the requested number of repetitions. Summarize rejects invalid repetition counts, missing trials, invalid run IDs, negative costs, missing repetitions, and duplicate run IDs. It groups trials by task, calculates task pass rates, computes the reported quantities, and totals recorded cost. Run_trials calls the executor for each task and run, then passes the resulting trials to summarize. The main block supplies fixture outcomes, prints the report, and checks 3 reported values. Connect the executor to the repository's existing sandbox runner and scorers, not to live email, calendar, browser, or database credentials. In the fixture, pass_at_1 is 0.9. Observed all runs task success is 0.5. Theoretical _power_k is 0.59049. Task rate variance is 0.01. And total cost is 0.045. These quantities differ. Observed all-run success is empirical, while theoretical pass power uses the independence model calculation from the aggregate one-run rate. With heterogeneous task probabilities, that aggregate calculation need not equal the average of task-specific P_i(k) values. Variance exposes heterogeneity that the mean hides. Missing repetitions and duplicate run IDs are rejected because unequal denominators invalidate comparison. Record calls input and output tokens when available, tool invocations, latency, judge usage, and retries, not only a currency estimate. 5 runs multiply execution cost and may multiply side effects unless tools are sandboxed or idempotent. 4 high-risk workflows spend extra samples first on booking, external communication, access control data, and cases with prior instability. 5 runs is a starting protocol, not a universal sample size. A deterministic calculator tool may pass identically 5 times while the surrounding agent remains unstable. So stability of one tool or task does not establish workflow stability. Conversely, failures correlated across all 5 runs can reveal a systematic rubric, retrieval, or tool contract defect rather than randomness. The artifact that changes in the real estate repository is the evaluator record. Add a repetition dimension and a reliability report to each suite version. The next release candidate should include the task level table, judge model card, calibration results, fixture and sandbox version, cost ledger, and retry and side effect policy. Engineers can decide whether to release, add a retry gate, narrow the supported workflow, or collect more evidence. This evidence supports a bounded decision about repeated execution reliability under the tested fixture and evaluator. It does not prove universal correctness, future distribution robustness, fair housing compliance, or safety under correlated failures, hidden state, change tools, or judge drift. Make stochastic behavior visible, budget evaluation runs, maintain deterministic fixtures, and turn reliability thresholds into release checks rather than anecdotes. Release Evaluator Suite v1 only with its validation results and a model card for each judge. The model card should state intended use, data and slices, known failure modes, calibration evidence, cost, and conditions under which the score must not be used. Evaluator Suite v1. Release the real estate score package before releasing the model. In the first dry run, the judge favored longer answers, allowing verbose responses with repeated listing facts and unsupported claims to beat short, correct answers. Making that package a CI gate would cause optimization for the judge instead of for buyers, renters, and agents. An evaluator is production code. It needs a package boundary, tests, a version, a cost record, a validation result, and an explicit maintenance policy. Without those artifacts, a score is an observation, not yet a dependable release signal. The package boundary. The real estate assistant already has task fixtures, response schemas, retrieval fixtures, and sandbox tool behavior from earlier chapters. Evaluator Suite v1 should consume those contracts rather than recreate them. Its durable core contains 4 layers, including the evaluator components described next. The suite includes deterministic code scorers for required field presence, citation validity, numerical consistency, policy flags, and tool contract compliance. It also includes calibrated model judges for qualities that require interpretation, such as whether an answer addresses the user's constraints. The registry names each evaluator, records its version and input contract, and identifies its cost and failure conditions. The report generator records each score by task, slice, system variant, evaluator, fixture version, and run, preserving the context needed to interpret results. Treat the registry as the release surface. It rejects evaluators with incomplete metadata, prevents replacing a scorer under an existing version, and makes reports reproducible from pinned inputs. A provider-specific judge adapter may sit behind this boundary, but the durable suite should not depend on an undocumented or changing provider interface. The repository example imports the established case contract from shared evaluator fixtures instead of defining a second schema. The shared contract is the repository boundary, while the registry and report code use standard library Python, require no credentials, and perform no external side effects. The code defines the versioned evaluator registry and its evaluator and run metadata contracts first. Registration validates required metadata, the code or judge kind, a major.minor.patch version format, a callable scorer, and a finite non-negative cost. It then rejects a duplicate name and version key. Evaluation validates non-empty run metadata, materializes the cases, and runs every registered score for every case. Exceptions, non-numeric scores, non-finite scores, and scores outside 0, 1 are recorded in errors rather than rows. Valid rows retain evaluator, case, slice, system variant, fixture version, sandbox version, and cost. The report also includes evaluator details, errors, system failures, and counts. The two included scores check a required fact and a bounded response length. The tests cover case-insensitive matching, missing facts, both length boundaries, duplicate versions, invalid metadata, NaN scores, and report pins, cost, and variant. If a test fails, the runner exits unsuccessfully. Otherwise, it emits the evaluated report as JSON. The shared import is deliberate because case adapts to the cumulative real estate response and fixture contract. That boundary must provide case_ID, expected, answer, and slice_name, or a thin compatibility adapter must provide them. The evaluator remains separate from retrieval, response, and sandbox behavior. A clean run has 6 passing tests and records the system variant, fixture snapshot, sandbox, evaluator version, and cost for each score. An empty errors list means measurement ran without evaluator failure. It does not establish assistant correctness. Exceptions and invalid scores go into errors, so CI can quarantine the measurement instead of turning a defect into a 0 or default pass. System underscore failures is reserved for failures attributed to the tested system, while evaluator implementation failures belong in errors. The tests protect the scorer contract rather than the whole assistant. Add fixtures for punctuation, missing fields, malformed outputs, adversarial text, and every policy-relevant slice. Structured output scores also need cases for invalid JSON, duplicate fields, null values, units, and contradictory facts. Malformed responses must never silently become passing defaults. Before release use, a judge needs a validation card covering the intended decision population, task definition, rubric, judge version and settings, prompt version, sample cases, human reference procedure, agreement and disagreement analysis, slices, blind spots, estimated cost, prohibited uses, and an explicit acceptance rule. Calibration must include counterexamples, such as a concise correct answer versus a longer answer containing an unsupported school quality claim. If the judge prefers the longer answer, the release artifact should expose that failure rather than conceal it in an aggregate score. A validation card is the evidence and operating contract for a judge. A model card covers the judge model's broader capabilities, limitations, and usage context, so it does not replace judge-specific validation evidence. A judge rationale explains the judge's output, but it is not proof of correctness or access to private reasoning. Version, cost, and drift controls. Pin the evaluator package, prompt, judge model identifier, decoding settings, parsing dependency, fixture snapshot, sandbox version, report schema, and source revision. Record usage and prices from the execution environment instead of relying on volatile prose assumptions. Changes to rubric wording, parser tolerance, retrieval fixtures, or judge configuration can change the measurement instrument, so assign a new version or document preserve compatibility. Define maintenance triggers in advance. These include excessive disagreement with human review, a new high-risk slice failure mode, change judge or provider behavior, schema, prompt, retrieval, or tool contract changes, an unexpected score distribution shift, rising cost, and repeated evaluator errors. Possible responses are recalibration, a new version, temporary quarantine, a narrowed supported population, or retirement. Thresholds must not be silently retuned to preserve a green dashboard. For the real estate scorer package, the changing artifacts are the suite manifest and its companion validation cards. The release bundle contains the registry, unit tests, pinned lock file, and source revision, fixture and sandbox identifiers, per evaluator cost ledger, report schema, judge calibration results, model cards, maintenance file, and a planned asset manifest. Evaluator Suite V1 Release Manifest. The manifest lists 4 planned assets. The evaluator hierarchy is checked for input contracts, versions, intended and prohibited uses, and failure conditions against the registry. The judge prompt template is pinned, tested on calibration counterexamples, and checked so rationales are not treated as proof or private reasoning. The calibration notebook records dataset and fixture versions, sampling, human reference procedures, agreement, disagreements, costs, and acceptance thresholds, and is rerun in a clean environment. The statistical reporting template checks denominators, slice definitions, uncertainty, evaluator versions, costs, and limitations without implying universal correctness or unsupported causal claims. The manifest is part of the release gate rather than a future documentation task. Every source file must be present in the companion repository, linked from the package README, and checked by the release checklist. Accessibility text must describe the information conveyed, not merely repeat a file name. Verification notes must identify the fixture, code, notebook, or report that was actually checked. The report can support a bounded comparison of assistant variants on the tested cases and slices under the recorded evaluator versions. It cannot establish universal factual correctness, future distribution performance, fair housing compliance, or safety when the population, tools, policies, or judge change. A required fact score may detect 2 bedrooms while missing a misleading implication about neighborhood demographics. Passing the scorer is not permission to generalize beyond its contract. This is daily work for AI engineers, evaluation engineers, ML platform engineers, product engineers, and safety engineers. Maintain interfaces, review fixtures, investigate evaluator regressions, budget runs, and decide whether evidence is strong enough for a particular gate. The professional skill is not producing a higher number. It is knowing what the number measures, where it fails, and which operational decision it can legitimately support. Release Evaluator Suite V1 only with its validation results, a model card for every judge, the judge validation cards, and a completed planned asset manifest. The governing takeaway is an automated score is trustworthy only to the extent that its evaluator has been validated for the decision population.